money. The individuals studied here are college students. They are asked to perform a challenging game, and this is what is recorded for each participant. It's the time that they waited before seeking help. It's a quantitative variable. There were different settings, and we are told that those settings were imposed at random. So we have three different conditions that the participants did not choose and were imposed at random. And therefore, we have an experiment with a completely randomized designs. This is important because it tells us that the three groups make three independent random samples, because the random assignment is going to assign participants to one of those three conditions at random. So the individuals in group 1 are completely different from and unrelated to the individuals in group 2, completely different from and unrelated to the individuals in group 3. So that means that we have three independent random samples representative of three different populations. We're interested in the mean of the quantitative variable, time to seek help, in three populations of individuals like those tested in conditions like the conditions tested. So that tells us that we have three mean U's, mu1, mu2, mu3. They represent all the mean time to seek help for a population of college students doing a complex game, but under three theoretical conditions. 1, after viewing fake money. 2, after working with money words. And 3, after working with neutral words. So that means that our null hypothesis, as a statement of no effect, is going to be that it doesn't matter what the conditions were, the time to seek help on average in this population under complex game situation is going to be the same regardless of what they were doing before the game. And so that means that our null hypothesis is going to be that mu1 is equal to mu2 is equal to mu3. No effect of setting on average. For ANOVA, the alternative hypothesis is completely neutral, non-directional, very general. It just says the null hypothesis is not true. Therefore, there is at least one of the means that is not equal to at least one other one. So it's just not true that they're all equal, which is very different from saying they have to be all different. So how do we check the conditions for inference? ANOVA has three conditions for inference. The first two are the same as for the two-sample t-test. We must have independent random samples and either normal data or large enough combined sample size. And then we have a third assumption for ANOVA, which is specific to it and has to do with the population standard deviations. So let's look at the first two conditions. We need independent random samples. We have determined that because of the design, we do have three independent random samples. Next, how do we check whether we have normal data or large enough sample size? Well, we do know that we have a total of 52 participants, so we should be fine even with extreme skew in the data, but let's nonetheless look at a distribution of our variable. So in this case, we have time in one column and then the label for the group, the condition in another column. So when we'll do, for example, a box plot, it will be grouped with time our variable, group for group. And we see that while the whiskers are fairly symmetric, except maybe in the third group, we do see that the median is closer to the first quartile always than to the third quartile. So it's very obvious that there is a little bit of skew in the data. Because we have a total sample size of 52, this is not going to be an issue. So then the third condition for inference has to do with the equality of population standard deviations. We can compare the sample standard deviations and check that they are similar enough to be appropriate for ANOVA. So if we go to statistics, descriptive statistics, again, our data is in groups. We see that the standard deviations here are all fairly similar because the largest one is 172.8, the smallest one is 118.1. So 173 is definitely less than twice the value of the smallest one, 118. So those sample standard deviations are similar enough that the third assumption for ANOVA is also met. So now that the conditions for inference are met, we can actually run the ANOVA F-test. which is going to be statistics, ANOVA. One way means there's only one explanatory variable, in this case, the pre-game conditions, and our variable is in the time column, and the groups are labeled in the group column. And that gives us the ANOVA table with the test statistic F 3.7 and the p-value 0.03, right? So 3.1% here. There might be times when you are not given the raw data, and unfortunately, Crunchit and quite a few other statistical softwares have not been programmed to give you the p-value from the summary statistics, unlike the one sample or two sample t-test, where you can do it either from raw data or from summary statistics. So how would you obtain the p-value from the test statistic? When you would go to distribution calculator, and this is the F statistic because it follows an F distribution, so we need to do a calculation under an F curve. Specifically, this F curve with degrees of freedom 2 and 49. 2 is because the degrees of freedom for the numerator, the first one, is going to be how many groups are we comparing? -1. So we're comparing 3 groups -1, so it's 2. And for the denominator, it's our total sample size, but we do lose 1 degree of freedom for each group that we're comparing. So here, 52 minus 3, that's 49. Our p-value is the probability if the null hypothesis of no effect was true, probability that we would then obtain a test statistic like this, or more extreme, which for an F statistic is always a larger value. So we are just looking for the probability that the F statistic is greater than 3.728. All right, so this is what the F distribution with those degrees of freedoms look like. And you can see that if the null hypothesis was true, we would have expected mostly F statistic values between 0 and about 2.5. Instead, we got 3.7, and this is getting to a point where there's very little chance of getting 3.7 or more. There's only a 3.1% chance of that. All right, so we have a p-value of about 3%. So we have reasonably strong evidence that on average, the time it takes college students to seek help in a complex game is associated with the setting of the condition. And because this is an experiment, we know that this is a causal association because there's nothing else to explain why there might be some differences. So it is affected by the priming condition before the game. So important to include on average here, because our null hypothesis was that mu1 equals mu2 equals mu3, and those are means, averages, that the conclusion applies to college students because in general, people's perception of money and how money affects them is likely to vary with the extent of their experiences with money. And college students, being young adults, are likely to have very different experiences with money than people who are established professionals or retirees, for instance. It's also important to say that this is specifically in a game situation, right? Because it does not necessarily imply that having some exposure to money words or images of money, like Monopoly, would actually affect people in everyday life, because other things like the long-term consequences, the repercussions of your actions in real life are much more substantial than in a game. I mean, in a game, people have more freedom to do crazy things or to be extremely competitive. It's not always a good strategy with your friends if you go a bit too far, but it's certainly not as bad as if you were to behave like that, like with your family in real life, for instance.